We'll wait for a few minutes and then we'll start, okay? Okay, so we'll begin. So I hope you all had a wonderful week and I hope I'm audible to you. Since we couldn't meet on Tuesday, so this is a compensation for the week two problem solving session. So let's begin. I'll share the screen and please let me know by message or something that if it's visible to you or not. I hope you can see it. Okay, thank you, Nisha. So we'll start. So again, once again, welcome to the course Geographic Information Systems problem solving session. So the instructor is Professor A.K. Saraf from IIT Roorkee, and I'm the teaching assistant Anshana from IIT Kanpur. So today we'll be discussing the week two mm, lectures and the problems related to that. And then in the upcoming Tuesday session, we'll be discussing the week three. This will be kind of a recap for you, so I hope that will be useful. So before going into the week two part, since it has been more than a week, so I thought it would be better if we have a small recap of the things that we had discussed. So we had discussed what a GIS is, that is Geographic Information System. So we have this definition that was given that it is a computer-based information system designed to accept large volumes of spatial data derived from variety of sources and to efficiently store, retrieve, analyze, model, and display these data according to user-defined specifications. I know this is a pretty big definition. We had all like cut it short and discussed it in the previous uh, discussion hour. So I just kept it here so that you can just rewind and think about all the things we had discussed and all the things you have read from the previous session. So if yeah, okay, then we can continue. I don't want to spend too much time in this topic, so yeah. And then we discussed about GNSS, then that is the global navigation system, and then under that we had discussed different GNSS platforms across the globe, like for each country. And then we had also discussed about the regional navigation system of India, which is Navig. So I had just briefly touched upon those topics. Then we had discussed the stages in a GIS project, like what do you do when you have a GIS project. So we basically define the problem, like what do you want out of this. We'll define the problem. Then according to that, we'll obtain the software and hardware, like software in the sense that we have a lot of open source software like QGIS, ArcView, then we have ArcGIS. So such softwares we'll take according to our need. And then of course we need a computer and related things, so that comes under the hardware. Then we gather all the data required, which can be satellite imagery, it can be all sometimes to generate digital elevation models. We need the elevation data, population data, for if you are focusing on the population density. So such data we'll gather. Then we'll sort it out, like we don't need all the information that we might be gathering, so we'll clean the data. Then we do the analysis, then we interpret and present the results. So this was the stages in GIS that was discussed. Then the components of GIS, you are already aware of it. So that is hardware, software, data, people, methods, and procedures. I'm just quickly going through this so that it doesn't get boring and it's something you already know. I'm just trying to recap the entire thing that we had discussed since it has been a long time since we last met. Then we discussed about spatial and non-spatial data, which we'll be discussing a little more detail in today's discussion because that's what we are focusing on. Spatial means geographic data, like something which is related to the location on the Earth's surface. That is spatial data, and we know that spatial data includes the raster data, the vector data, and the TIN data, that is the triangulated irregular network data. So that comes under the spatial or geographic data. And if you remember, in vector data, we had discussed in the previous session also. So vector data includes points, lines, and polygons, unlike raster data or TIN data. So that we'll be discussing a little more in detail today. Then we have the non-spatial or tabular data, which does not necessarily imply the geographic location or anything, but rather it gives some more information regarding that particular the GIS model that you're developing. So it can give you information. For example, if it's about the our country map, India map, so then it can give you information about the different states and maybe information about the population in different states or the administrative borders, such things. So that all comes under tabular data. Like if you have used GIS software, or maybe in further sessions we can compile everything and I can show you one in QGIS. So if we check a particular project, like if you check a particular layer in the sense that, for example, if I have India map, okay, and I want like India map with the state divisions. Like I have all kind of state divisions, and then if I click on the layer and I look at the attribute table, I might get the information of all the states, although it might not be mentioned in the map as such, but then you can get all those information in the attribute table or the tabular data. Okay. Then we had discussed about topology, which describes the spatial relationships between adjacent features. So, and like if you remember, we had a um, okay. So if you remember, we had a topological data and non-topological a comparison was there. So in that I had said, like, if we are not considering the topology, I'm sorry, this is okay. So if we are not considering the topology, or if this is a non-topological data, then what will happen is, let's say this is one feature, this is A is one feature, B is one feature, and then you're trying to bring it together, you will find such gaps generated if the topology of this is not considered. But then if you consider the topology, the same thing you can generate, in which the boundary is only stored once, so that you don't get another gap, or this gap can also be considered as another polygon. So such confusion will not arise if topology is considered. So topology is basically a collection of rules that, coupled with a set of editing tools and techniques, enables the geodatabase to more accurately model geometric relationships. So it's like although we talk about points, lines, and polygons, what happens is that the image or the the project that you're working on might be a combination of all these three. So at times you will have to understand the relationship between adjacent features. So for that purpose, this topology is very much important. So this brings us to the topics that we are going to discuss today. So the first one is raster data. So we had already discussed about vector data. So today we'll be discussing about raster data. So in raster data, the images, like raster data is basically the images that you see. Like you take a picture, a photograph. So that image is basically your raster data. Okay. So this raster data, in that it stores images as rows and columns of numbers with a digital value or number for each cell. That is basically, if you look at this diagram, or rather I can just draw okay, I'm trying to make it as square as possible, because the basic unit will be always in the shape of a square and not anything else. But yeah, that's something you have to understand, although my picture is not very like giving justice to that. So yeah. So what I'm trying to say is, the image will be stored in the form of, these are rows. Oh, I'm sorry. Okay. So the image will be stored in the form of rows, that is, these are rows, and these are, I don't know what is happening, and these are columns. Okay. So in the form of rows and columns, so these it's kind of analogous to a matrix, we can say. But what you have to keep in mind is that each of this, like each cell, this one is one cell, This is another cell. So each of these smaller units, or which are known as cells, they have a unique or a value of its own. So that value we call it as the digital value or the digital number of each of the cell. Okay, digital value, or rather you write it as DN, digital number, for each cell. So the units that I said are usually represented as square grid cells that are uniform in size. Okay, it's always square. But why this is specified is because at times what happens is you can also have a rectangular image. Okay, so the image can be rectangular, it can be square, but what you have to keep in mind is that the fundamental basic unit, that each cell will be in the form of a square. Although the output, the raster image might be square or rectangular, but then each of the units are square in shape. That thing you have to keep in mind. So if we take a look at this, okay, I'll just hide this. Okay. Okay, so if we take a look at this, you can see that you have a vector data output of an area and a raster data output of an area. So from this, you can actually see the difference. Okay, so here you have the polygon. This is a polygon. Uh, and okay, all are represented kind of in a polygon shape. So yeah, let it be. So this is what gives you the idea in a vector form. And if you take a look at the one on the top, which is the raster data form, here you can see that everything is denoted in a grid format. So this blue continuous this thing that you're seeing, in this case it is like in the form of uh, each of the cell units are representing that. Similarly, this part is represented like this is represented like this is more of a geometric shape, and this is more uh, you can say not very geometric, because if you see this shape and this shape, this is a little more irregular polygon, but then here you can see that it is a square, and similarly this one. So that is regarding the vector data and the raster data, and I will definitely discuss the differences so that you understand why like we are using both data sets. Okay, so I hope the basic idea is clear. So in raster data, the data is classified as continuous or thematic. So what is continuous? The one that you see in this image, no? Here you can see. So like it's not like this green is there, and as soon as the green ends, you have a gray color, and here you have a brown, or you can say red. Here you have a blue, so that it's a continuous data set like the one you see in an image. There is no discreteness that you can see in the image. And then you have a thematic data, raster data, where each cell denotes a feature type. The example I will show you, but thematic is basically you can um, I think the example can be given like thematic maps. I don't know if you're familiar with it. Like I think in land use, land covered maps that you generate, that is based on like vegetation set. Vegetation we consider as one class. Then we have the water body as another class. Then we have the soil as another. So such features are distinguished basically in the thematic data set. And there are numerous data formats. This you might have at least heard of these things. That is the TIFF image, and like TIFF is basically the tech information file format. Then we have the GIF. Obviously, you might be familiar with the GIF because whenever we are especially in the messaging platforms, we use this, right? It's kind of like an animated image kind of thing. Then we have the image, then we have the JPG, PNG, all these numerous data formats are there for the raster data. So as I said, it represent features as a matrix of cells within rows and columns in a continuous space. So then sir had discussed about the digital elevation model. This will be further discussed in much more detail. So here I'm just giving you an introduction to what it is. But obviously in the upcoming lectures, we'll have a further detailed discussion on the digital elevation model. So a digital elevation model is a computer generated 3D representation of the Earth's surface. It shows the height, elevation of the land at different points. However, as if you remember from the lectures, the professor has also mentioned that it need not be elevation all the time. At times, it can be like it depends on the purpose. That's what I said. You need to know the aim of or objective of your what do you say, your project. So if at times in place of the elevation, you might have to consider the pH. So but generally the digital elevation model on general aspect, it is related to the elevation. And as you can see here, this is a digital elevation model that was generated. So here you can see this blue region that indicates the dips or the valleys, and this red region that shows you the elevated areas or the mountainous area, terrain, whatever it is. So that difference we can see in this. Okay. Next topic that was discussed was the image-based data. So image data ranges from satellite images and aerial photographs to scanned maps that have been converted from printed to digital format. So image-based data is like, this is also something that all of us are familiar with. Although we might not know the classification, but we are familiar with this, right? So if you go to a place that you are completely unaware of, or it's a completely new place, the first thing that what we'll do is we'll take the Google map or the Google Earth image to see, get an idea of the area. So such satellite images or even aerial photographs. Aerial photographs are captured from airplanes or using this what do you say, this drones or using helicopters or any such devices. It's not at a very high elevation, so that's why we say aerial photographs. So it can be satellite images or aerial photographs, and even the maps that we have, hard copy, that can be scanned and converted to the digital format. Such data set, we call it as image data. We are making data like the location data from an image. So for example, if you have an image of your area, you can actually put it in, it might be just a photograph, okay, an aerial photograph you can say. So if you want to geo-reference it and know like its exact position with respect to the latitude, longitude and everything. So for that purpose, you can put that image or upload that image in a software, GIS software. You can mark the ground control points. Like ground control points is basically for example, let's say you have an image, you have certain buildings here, uh, and maybe some river flowing, so all these things. So what you can do is you can basically georeference it. So georeferencing, first you have to establish the ground control points. Okay, so ground control points, how do you establish it? Like an easier method is, if you already know the location of each of some points in this image, you give those consider those points as ground control points, give the lat long information, and then you can georeference it uh, in the GIS software by also giving the appropriate coordinate system. But I think that I can demonstrate in maybe one of the sessions that we'll have later on, so that you will understand what I'm trying to say. Some of you might already be familiar with it, but then for those who don't know, maybe I can show that using the QGIS software in one of the upcoming sessions, or maybe in the last one. Then they had discussed the difference between an image and a grid. So the uh, image versus grid, what you'll see is image is something, or rather this pixel is something that you are more familiar with. So I think, for example, if you are buying a phone now, we and you are very much interested in photography, then you'll look at the pixels, right? So we have even have cameras with 48 megapixel like that. So in images, the basic fundamental unit is pixel, okay? And in case of grid data, the basic fundamental unit is the cell. This image or the pixel will only have the positive integers as its value, while the grid image or the grid data set will have both positive and negative integers and even real numbers. So that is more inclusive. Image is more like it's not very sophisticated. It's something very easily understandable and accessible, unlike the grid data set. So most of the time what happens is this pixel will be giving us information regarding the let's say like reflectance or energy information. Like for example, how the if you look at a image, you can see regions where the sunlight is more prominent, where you can see shadows and everything, right? So such reflectance variations or the energy variations will be noted in the pixels. So that's why it's almost always in terms of positive integers, and the value will all mostly vary between 0 to 255. The values will be like the number will be 256, and it ranges from 0 to 255. Okay. And in case of grid cell value, it's basically like, for example, it might be considering a specific feature, like for example elevation. So in that cell value, it will be telling about the elevation of that particular cell, not necessarily the reflectance or the energy variation. So for example, why they're saying this positive and negative integers like that is that if you imagine you're mapping an area which is very close to the sea, let's say, and you might have certain locations which is, let's say this is the sea level, okay? So you might have certain locations or objects that are above sea level, and some that will be below the sea level. So most of the time the positive integers will be given to the features above sea level, and the negative one will be given to the features below the sea level. But one thing you have to keep in mind is image based data or the grid based data both are essentially raster data models, but the complexity is a little different. Like image is more simple compared to the grid data. Then sir had discussed about spatial resolution. So the measure of how closely pixels or cells, because as I said, we are discussing about raster data model. So in that either pixels can come or either cells can come depending on the data that you're handling. So here we are giving a general overview. So spatial resolution is basically the measure of how closely pixels or cells can be resolved in an image or grid is called spatial resolution, and it depends on properties of the system creating the image or grid. So like in simple terms what I'm trying to say is let's say this I think if this image will be easier for you to understand. The clarity of the image or grid is decided by its spatial resolution. So if you take a look at this image on top has more grids or cells, whatever it is, like pixels or cells over here, which means that image the image with more pixels or more cells will give you more information, or it will give you more clarity. Okay, so more properties are being accounted for, so we call that as high spatial resolution image. And the ones in which the grid cells sizes are larger and the grid cells are less in number, we call it as low spatial resolution. So this is a diagrammatic representation, and a real life representation is shown on the right. This was also given in Professor Saraf's slides. So here you can see this is high spatial resolution. Here you can actually see the buildings, the roundabout, you can see the tree line, you can see all those different parameters is very clear in this. But when you take a look at the medium spatial resolution, which means the grid numbers has reduced in this, okay? So grid numbers has reduced, so it's barely understandable. Like from the color, you can barely understand, okay, some different features are there, but not exactly like what is there. For example, here, I think these are vehicles, okay? Here, that is not at all visible. Here, the only thing that you can distinguish is the houses and maybe the street, but not other intricate features. So in medium spatial resolution, that much of information is not available. And then when you come to low spatial resolution, nothing is basically clear. It's very pixelated. Okay? So that is why, like, if you take a photograph from a, let's say, a phone with less pixels, so then what happens is, if you zoom that image, you might have noticed that at one point the information will be completely lost. You will not understand what that image contains. But if you have taken that photograph in a very good phone with a good pixel, like megapixels, then what happens is, no matter how much you zoom, the clarity will be to some extent retained. For example, the recent phones like the iPhone, I think 16 or something, and then even Samsung's S23 Ultra, their main marketing was basically how far you can zoom without losing the clarity and information. So that's what basically spatial resolution is trying to convey. So here is an image that will give you an understanding about how this raster data and vector data is different. So this is a real world image. It's a very black and white image. So in vector, what is basically how we are representing is this, I think, is a road or might be a waterway. I'm not very sure. Anyway, it's a polyline data set. And here, this is a building. So this building is denoted as a polygon. Okay, they have not focused on the other features, so we are just focusing on these two. So this is how a vector data will represent this image from real world. And when you look at a raster data, it involves rows and columns with a either grids or pixels. So in that, we have this image represented like this, okay, in terms of squares. This is a little simplified, but the problem is that it will not at times account for the continuity. So this is the difference between the raster data versus the vector data. So vector data, if you remember, we had discussed, it gives you information about points, lines and polygons, and which are stored as a collection of xy coordinates. We had discussed it in the last session, okay? So you can just go through that once again if you have forgotten. But it's basically vector data set discusses about points, lines and polygons. And in comparison, the raster data divides data into grid cells. So several grid cells will be present, which we have just seen, okay? Then vector data is mostly, because we are using both data set, right? Like, it's not that one is better than the other. It depends on your requirement. Basically, the people's requirement is what sort of defines like which data set we have to use. So in vector data, it is useful for describing discrete features, but less useful for describing continuously varying features such as soil type. So uh, I hope you are able to understand that difference in the vector and raster data. It's basically, for example, here we are just noting the building and the path, whatever it is. So that is fine. Vector data is giving you that information. Suppose we were looking at a very open land in which soil type is varying. Okay. But in vector data set, you cannot basically differentiate between the different soil types. It's a bit difficult. But if that continuous variation it needs to be recorded, for that purpose, you will have to use the raster data set, because each grid has its own unique values. So if the soil type is varying, Then according to that, the grid cell values will also vary. So as a result, the raster data can account for the continuously varying soil type, but the vector data cannot do that. Okay, that is the difference. This raster data can model continuous features. However, vector data can model the discrete features much better than the raster data. Then the accurate positional information that is best for storing discrete thematic features like roads, shorelines, seabed features, all that can be done by vector data. But that's not very feasible in case of raster data, because sometimes the raster data simplifies the features a little bit if it's not continuous. So it does not very well account for the discrete features, as you can see here also. The if you make a comparison, this one represents this feature better when compared to the raster data, right? So that's what I was trying to say, like it depends on your requirement. In raster data, the satellite information can be easily incorporated, but that is not the case for vector data. Vector data, it's like first you might have to define the features, then overlap it with the mm, satellite information. So it's a little bit more uh, comparatively more complicated, but in case of raster data, that information can be easily incorporated because it's mostly image data, right? Image data or grid cell based data. In vector data, the boundaries are very neat and clean, but here the boundaries are not neat or clean. So the boundaries are well defined over here, but here it's not that well defined. Because here you can see this much region, for example, if I try to draw this, it might not be very accurate, but I'm trying to draw that feature. So here you can see, right? This much, that white area is not at all accounted for in the raster image. So that's what they're trying to say. Boundaries are neat or clean in case of vector data, but boundaries are not neat or clean in case of the raster data. Here also it's shown. This is an image that I taken from one of the slides. So here you can see all these boundaries are well accounted for, but here there are certain features, either it is overestimated or sometimes it is underestimated. So it's not very clear when compared to this is the vector data, okay, and this is the raster data. Then another thing that was discussed was that you can convert this raster data to vector data or vector data to raster data, but the problem is that uh, not all the information might be completely incorporated. Like there will be degradation of the data quality to some extent, because at times what happens is vector data might have a lot of information, which when you convert to raster, so raster might omit certain information from the vector data to get a more smooth image. So once visibly it might not be as much, but then when you look into detail, then you will see some loss of data. So the issues include loss of detail, then loss of accuracy, then stair stepping, that is raster to vector. When you do that, such problems can arise. Then changes to the original data. So raster, so in a summary, you can say that raster is faster, but vector is more correct. So if all you need is to see a location or for navigation purpose for that matter, then only raster data is sufficient, right? You can just do that. Like you just need to see the area, you can travel, whatever it is. But if your purpose is different, like if you have to map an area or something like that, then you might need the vector data, so which is more correct and accurate. So that brings us to the another spatial data, or rather the out of the three, this is the last one that we'll discuss. So that is triangulated irregular network data. Okay, so we had already discussed the vector data, then raster data we discussed. Now to the next one is the TIN data, or the triangulated irregular network data. So a triangulated irregular network or TIN is a way to represent the Earth's surface using triangles. So if you remember, vector data, we had used points, lines and polygons, and raster data we had used grids, right? But in case of TIN data, we will be using triangles. But why do they say that triangulated irregular network is because in raster data, if you remember, we know that each of that units are similar to each other, right? But in case of triangulated irregular network, the triangles might be of different uh, length and size, and like it's very irregular, it's not regular. Like all the triangles are not of the same size, it can vary. Some can be big, some can be small, so that is why we call it as triangulated irregular network. So this is basically formed or made by connecting points with known elevation values to form a network of non-overlapping triangles. I think I have an image in the upcoming slide. If either way, I'll just show you. Like this is our point data, let's say. Okay, we have just random points here, which is giving us information about elevation values. So according to the requirement, what when you do make a triangulated irregular network data, what we'll do is we'll connect the elevation values which are related to each other, and then accordingly generated the triangulated network data. So we are just connecting it. I'm just randomly doing it, but then when you're actually doing the modeling, we are doing this based on the related elevation values, and we'll also ensure that none of the triangles are overlapping. Okay, so this is somehow it kind of represents a triangulated irregular network data. Within each triangle, the surface is represented by a plane. Basically this one, okay, this is one triangle, so this surface is represented by a plane, and the triangles are made from a set of points called mass points. So the points that I had drawn earlier, we call them as mass points, and from there we generate the TIN data. This is the image. So here you have the TIN. This is the vector image, you can say, and this is the raster. Yeah. So from these points, if you are generating the raster data, it will sometimes come like this, and if you are generating the TIN data, it will come like this. So they have connected the points according to the related values and then generated the triangular irregular network data. So although like you're now familiar with all these three data sets, like the vector data set, the TIN and the raster, which are the spatial data sets. So we know why we use the vector data. We also understood why we are using the raster data. Now where do we actually use this TIN data? Okay, so the TIN data, it better represents, I hope this is understandable. Okay, it better represents relief roughness or a rugged terrain. Okay, so it's basically if you are mapping a region, like let's say the Himalayas. Okay, if it's a plain region like the Indo-Gangetic alluvium or something, where you are not having that much of a relief difference or anything, then even the raster data set is sufficient. That is more than enough to understand the region. But if we are exploring the Himalayan region, which has a lot of relief variations, like you have a lot of mountains, valleys and everything, I'm getting a notification that this call will end in 15 minutes. So I think that is the 1 hour duration something. So I'll again restart the meeting. Kindly please rejoin it's using the same link. Okay, I think this might get over because of, I don't know why. So anyway, I'll continue for the 15 minutes and then once again start it. Okay, so as I was saying, so if we are mapping the Himalayan region, which has a lot of mountains and valleys, so then in such cases, we'll prefer the tin data. That is, it will better represent the relief roughness or the rugged terrain. Okay. So this is the tin terminology. So the ones like we have one over here and I had drawn one over here. So uh, basically this point that you have over here, and in every triangle also we call this as the vertex, right? So that is the triangle vertex. Then here we have this planar region, that is the triangle face. This is the triangle edge. You can see. Then this is the convex hull, that is basically the kind of the you can say the outer periphery, you can say, and then this region is the outer region. Okay, so this is the convex hull, this is the triangle edge, this is the triangle face, and this is the triangle vertex. That is just basic terminology, just for information case. Then this tin data, that everything is organized in the form of tables. Okay, for in a tin data. I'll do one thing. I'll once again restart the meeting in like 2-3 minutes so that it doesn't stop automatically. So once we'll discuss this, I'll once again restart it. Okay, please rejoin using the same link. Okay, so as I said, in the tin data, everything is organized in the form of tables. So if we take a look at this one, okay, so we have a node table which lists of each triangle and its defining nodes are given. So here the triangle information is there and the node is given here. I'll tell you what it is. Then we have the edge table. So this is the edge table that lists the 3 adjacent triangles for each facet. Okay, so adjacent triangle information is here, the triangle is here, or the facet is here. So according to that we'll get the information on which all triangles are adjacent to it or not. Then we have the xy coordinate tables. It stores the nodes coordinate. So node information is here, coordinate information is here, and then we have the z coordinates, which more or less tells you about the elevation or the depression or whatever it is. That difference will be given here. So again the node and the coordinate. So we'll see an example. Let's say if we look at C. Okay, so C is here. So C is the triangle and the node associated with C is 1, 2 and 8. So if we take a look at this, so it's given as 1, 2 and 8. Okay, these are the nodes. And maybe one more we can see, like let's say something in N we can see. Okay, N. So N is over here, and the nodes related to N are 7, 10 and 11. So if we take a look at it, we can see 7, 10 and 11 are the defining nodes for N triangle. Okay. Then we look at the edge table. So in the edge table, we have the list of the 3 adjacent triangles for each facet. So we'll we'll take the D triangle. Where is the D? Okay, this is the D. So for D triangle, the adjacent triangles for this is like this face is E is there, and then we have C. Okay, so C and E are the adjacent triangles for this. Only 2 are there. But if we take a look at G, so this is G. For this facet, we have F, M and H. So F, H and M are there. So a minimum of 2 and a maximum of 3. That is the only information that you're going to get in the edge table. Nothing more or less than that. Okay, minimum 2 and maximum 3. Then we have the xy coordinate table. It stores the nodes coordinates. So nodes coordinates is like x1, y1, x2, y2. That is like for one first node we call it as x1, y1, second node it is x2, y2, and then for the 11th one we call it as x11, y11. Similarly, z coordinates also. Like for the first node it is z1, second is z2, and then when you get to like the 11th node it is z11. So all these information will be given, tabular information will be there for a triangulated irregular network data set. If you remember, in vector data also we had discussed a similar uh, table, right? Like each of the phases, polygons, lines and all those things we had discussed. So similarly for tin data also we have such information. Then the disadvantages and advantages of the tin data was discussed. So the disadvantage is that it requires a lot more processing to generate the tin to even start. Like for us, the elevation data, the processing is a little more when compared to the other two data set. And then errors can happen along the edges if it is not very well accounted for. But the advantage is that the terrain parameters like the slope and aspect is mainly, you can just relate it to a slope direction. Okay, so the slope and aspect calculated for each of the triangle and stored as an attribute of the facet. Okay, so each facet will have the attribute of slope and aspect. So such terrain parameters can be very well accounted for using the tin data. For areas of complex relief, tin works better than the raster, because I don't think I've included the image, but if you had looked or gone through the lectures like from Professor Saraf, if you remember, there was an image, like its raster was also shown, and its tin data was also shown. So some terrain features were present over here, which was not very well accounted by the raster image. But tin had accounted a lot more detailed version of that terrain features. But at the same time, some planar features were there which were better represented in the raster image when compared to the tin image. Tin image, that was a little uh, blurry, but then in the raster that portion was a little more clearer. So that's why they're saying like advantage of tin is more in case of the terrain parameters, terrain features or irregular surfaces rather than the smooth surfaces. Then more detailed representation for higher density of data points. So like minute changes in elevation, all those things can be accounted for by tin. That is why processing is also taking more time consuming. Then breakpoint features are also more accurate, like ridge lines and valley bottoms. Like if you have a mountain, this ridge line will be well accounted for, then the valley bottoms will be well accounted for. With that might not be that much considered in case of the uh, raster image as compared to the tin data. Okay, and this they had just given a definition for the facet. Facet is basically the triangular face in a triangular irregular network. Okay, I'll just restart this meeting because it's showing that the call will end in 6 minutes. So I'll just once again restart the meeting, and then uh, you guys please join back. Okay. Hmm. Okay, I'm not able to extend it. So I'll stop and I'll again start. Okay, somebody had asked about rugged terrain. Rugged terrain is like something which is not smooth. Okay, like there is a lot of up and down like that. It's not very smooth. I'll show it once I restart the meeting, okay? And Z coordinate accounts for the height, the elevation. Like it can be something which tells you about the height or some deep points. That also I'll show you once I restart the meeting, okay? I just saw your messages. It's again showing that the call will end in 4 minutes. I think that call has to end and then only I can restart. Okay, so okay, for the timing, I'll just anyway, I'll just anyway continue and then when it ends, I'll try to restart the meeting again. I don't know why it's showing like that. Last time it was not an issue. Okay. So this is the differences that sir had given in the lecture. So he has pointed out the advantages and disadvantages of tin and raster. So the advantage, as I said, in tin, the ability to describe the surface at different level of resolution. The same image, you can actually see different levels of resolution. And there is more efficiency in storing the data, but it might be a little more that processing might be a little more confusing and more complicated, and then also the data might be also quite heavy. But when compared to that, raster is easy to store and it is easy to manipulate, like the images that you have right on your phone, so that is easier to handle compared to the tin data. And that is easy integration with the raster databases, and it is smoother, more natural appearance of derived terrain features. And the disadvantages is that in many cases it require the visual control and manual control of the network, while in the rasters the inability to use various grid sizes to reflect areas of different complexity of relief. Because in raster, as I said, one raster image will have that cells of same size. So if some terrain different something is there, most of the time those cell size cannot be varied, so that will either be just omitted or it will not be given in much clarity. But that in case of tin you can see. Once this call ends, I will again restart it, and then maybe in Google Earth I can try to show this. I'll try, but I'm not very sure how this works. I'm not starting a new topic because I don't want the discussion to break. So just give me a minute. Once the call ends, I'll restart. Okay. I'm really sorry for the inconvenience. Okay, so as we were discussing the tin and the raster data set, uh, yeah, so we have already discussed the advantages and the disadvantages, and I'm really sorry, like I don't know what happened with the link. So from next session onwards, I'll already share another meeting link in the beginning itself, so that you can immediately join that link as soon as our first 1 hour gets over. We didn't face this issue last time. I don't know how it came about this time. I'm really sorry for that. Okay, so we were discussing about the soft break line and the hard break line. So the definition for soft break line is that a line that gently influences terrain shape without sharp elevation changes. Okay, so there is not much of a elevation change that is very significant. So for that we will use the soft break line. But some in case where the elevation difference is very distinct or very sudden, like a sudden slope or an elevation is shown, in such cases we'll use the hard break line. So the effect of on surface is the that it smoothly adjusts terrain features while maintaining a natural flow. Okay, like it will not be very evident, like everything will be smoothly kept, but then at the same time you can see a slight variation also. But in case of hard break line, it creates a sharp noticeable break in the terrain. This soft break line is used in case of gradual transitions like gentle slopes, ridges or road center lines. But hard break line is mostly used in case of cliffs. Cliffs is like a sudden slope is coming, no? So in cliffs, river banks, roads or retaining walls where elevation changes suddenly. Okay. The impact on tin is that the soft break line does not interrupt the continuity of triangles, but hard break line enforces strict triangle edge adjustments to match the terrain breaks. Just give me a moment. Okay, then this brings us to the next topic, that is the non-spatial data. Okay, so non-spatial data, we have basically six kinds of basic attribute data that are used in the GIS. Okay, so non-spatial data can also be called as tabular data or attribute data. So it is classified as nominal or categories, ordinal or ranks, interval, ratio, cyclic, counts and amounts. Okay, these are the six basic kinds of attribute data. And first we'll discuss the nominal or categories. So the simplest type of attribute described by name and to identify or distinguish one entity from another with no specific order. Okay, so that is like example like in land use land cover thing, so you will be defining the land area, then you might be defining the water body, then you might be defining the forest cover, you might be defining the built up area. So that's just you're giving a name or a category to those to represent those features. Okay, or you might give the place names or name of houses or the numbers on a driver's license. So such it's like it's not given in any specific order, it's just you're giving assigning some names, that's it. So the nominal attributes includes numbers, letters and even colors. Okay, it can be anything. Then it brings us to the ordinal or the ranks. Unlike the nominal one, here you have some order or some hierarchy kind of thing. So here you have a list of discrete classes but with an inherent or natural order or sequence. Okay, there are discrete classes but then they have a proper order. For example, if you are representing a map in which you have a lot of streams going. Okay, so you have one stream like this, one going like this, then like this. So this will be of first order, then this will be of the second order, then this will be of the third order. So like that, that first order, second order. So you're actually giving a natural order or sequence to the streams. So that is ordinal or ranks. Then we have level of education. So you have the primary, secondary, like that. So there is some kind of classification there. Unlike the, not classification, some kind of uh, hierarchy, or basically the order that you're giving, rank that you're giving. Okay. So ranks put features in order, that is from high to low. They are used when direct measures are difficult or if the quantity represents a combination of factors. So agricultural land can be classified based on the soil quality. Like one that is best can be given as 1. The class 2 is not so good. Then as you go to maybe let's say class 5, it's just not that good. Okay. So like that, you are categorizing the uh, what like the soil quality. So that is, you're assigning the ordinal or ranks. Then we have the interval. So attributes have natural sequence, but in addition the distance between values have meaning. Okay. So here uh, a sequence is there, but then between values also some understanding should be there. Understanding in the sense that let's say if on a Celsius temperature scale, you're considering the interval between 30 and 20 and 20 and 10, that will be different, right? Like 30-degree and 20-degree, that difference will be different from 20-degree and 10-degree. So that difference is accounted for in the interval. Okay. Then we have the attributes have the same, then we are discussing about ratio. So that is basically attributes that have the same characteristics as interval variables, but in addition these have 0 or starting point. It's kind of like interval variables, but then here we have a 0 or a starting point. It's not like randomly you're taking between two like two numbers. Okay. So here the let's say like weight is the ratio. So because it makes sense to say that a person of 100 kg is twice as heavy as a person of 50 kg. That is understandable, right? 50 kg, 100 is like twice of that. That is understandable. But if you say like in case of temperature, if we are saying that 20 is not like 20 is twice of 10, that is not right. Okay, 20 is not as twice as hot as 10. Okay, so in such cases we'll have to use interval, but where that comparison can be made, we'll use the ratio. Then we have the directional or cyclic category. So that is flow direction on a map or compass direction or longitude. So here the special problem is that the number will be following 359 will be 0, like 360 degrees, you know, right? So it starts from 0, then as you reach 360 degree, then again you are getting 0. So such confusion can arise. So in case of in this GIS softwares and all, if often we write lat long in DMS form, that is degree, minutes and seconds, but uh, in such softwares, like computers are not normally able to deal with the fact that adding 1 minute to a latitude of 30 degree 59 minutes produces 31 degree and no minutes, like 0 minutes, and not 30 degree and 60 minutes. Like if you're directly adding that 1 minute to this 30 degree 59 minutes, that is not right. Okay. So therefore, a normal way of dealing this with this problem in GIS is to express lat long in terms of decimal degrees and not in terms of degree, minute and second. So 30 degree 59 minutes will be stored as 30.988, like that. So that's why when you add 1 minute to it, then that becomes 31 degree and 0 minutes instead of 30 degree and 60 minutes. Then we have counts and amounts. So counts and amounts show the total numbers. A count is the actual number of features on the map. Like for example, uh, let's say like district wise population is an example. So you have a state map or a district, a state map in which you have the districts represented. So each of the district you have determined the population. Okay, so that population class you have defined, like from this population number to this population number is belongs to this category. So like that. Okay, so that is and an amount can be any measurable quantity like the number of students in a class. So using a count or amount, it lets you see the actual value of each feature as well as its magnitude compared to other features. Okay, so example is as I said, district wise population. This brings us to the problems, and at first we'll discuss the solutions to the week 1 assignment, then we'll discuss the solution to the week 2 assignment because it's already given. That's why I'm discussing, but then otherwise, like for example, if the solutions are already not discussed or given in the portal, then we will not be discussing that because that can result in cheating or something. So in order to avoid that, we will not be discussing any assignment prior to its solution being given in the portal. Since it's already given, I'm discussing that. Okay, so GIS is dash and dash technology. Okay, so the geographic information system is regarded as what? The options are digital and analog, spatial and analog, digital and spatial, spatial and manual. You guys can either tell me, or you can even put it in the chat so that I know like what the answer is. Any idea? Okay, so the answer is digital and spatial. So GIS is a digital and spatial technology. It digitizes the information that you give based on the spatial distribution or based on the location information. Three basic kinds of vector entities are. This is very simple, like we have already discussed it. I have recapped it multiple times. So yeah, the answer is point, line and polygon. This brings us to the next question. GIS, remote sensing and GPS technologies are what sort? Like we had discussed this in the first problem solving session when we were discussing GNSS, GIS and remote sensing. GPS is something which is more familiar because of which we have given it like that, but a wholesome term would be GNSS. Okay, so the answer is generic, digital and spatial. Then topology describes the dash relationships between adjacent features. This is also very simple because at least that this is one of the terms I've been frequently using throughout all these sessions. Yeah, so the answer is spatial. Okay, topology describes the spatial relationships between adjacent features. Which of the following is not an example of spatial data? Like we know what spatial data is, right? So which of these are not an example of spatial data? Okay, so the answer is times of particular events. Time cannot be accounted for, but rather the location, route, polygons, all those things can be accounted for in a spatial data. The geographic information system is a dash-based information system designed to accept large volumes of dash data derived from variety of sources and to efficiently store, retrieve, dash, model and display output these data according to dash defined specifications. This is essentially the definition that was given. So you just have to fill in the information that you already know. I know it's a bit long, but then yeah, you're already familiar with this. Okay, so the answer is computer, spatial analysis, and user. User defined specifications. You retrieve, analyze, right? Large volumes of spatial data is used, and it is a computer based information system. Attribute data are one type of spatial data, and you just have to tell me whether it is true or false, because we have already discussed about spatial data and non-spatial data. So in which category does attribute data come? Think about that, and then that gives you the answer for this. The answer is false, because attribute data is a type of non-spatial data. It's not a spatial data. Name the 5 components of GIS. This is very simple. We have already discussed it while recapping, and also otherwise also you are very familiar with this. It is hardware, software, data, methods, and people. These are the 5 components. Okay, hardware, software, data, methods, people. Okay, this brings us to the week 2 part. So the first question is, how many basic kinds of attributes so far is known in GIS domain? We have discussed each of them towards the end, so you can just recollect it. Okay, the answer is 6. Okay, we had discussed it, right? The nominal category, the direction or cyclic, then we had the counts, all those, like 6 of them we had discussed. So a nominal attribute can be any, like which one? Like it can it be only numeric, or only alphanumeric, only alphabets, or all of that? Yeah. So a nominal attribute can be numeric, alphanumeric, and also alphabets. Ratio attributes have the same characteristic as interval variables, but in addition, these have what? Like we had discussed about ratio attributes, right? Like the weight comparison, like a 50 kg person and a 100 kg person. So 100 kg person will be twice as heavy as the 50 kg. So like that. They have a 0 or starting point. Okay. In tin model, triangles are made from a set of points called what? This also we had discussed. It is mass points, okay? I had drawn and shown you, right? Like there are this several points, like this might be the vector data set. Then when you join that, you make the triangulated network data. You can join like this, this, like this. It can go like this. So all these points that I had drawn initially, they are known as the mass points. The tin model stores data in which form? Like we have the node table, the edge table, the XY coordinate, and the Z tables. It's very easy because I had described it just now, so I hope you didn't forget it. Yeah, the answer is all of the above. In all these formats, it stores the data. In model data, a lectin model is adaptable to surface roughness. True or false? Okay, the answer is true. Okay. It is not possible to make subset of points, raster, tin, or polylines. Which of these can you not make a subset? In tin, it's not possible to make a subset, but in the other cases, it's possible. Okay. The measure of how closely pixels or cells can be resolved in an image or grid is called. This also we have discussed. Yeah, right. The answer is spatial resolution. The dash model is extremely useful for describing discrete features but less useful for describing continuously varying features. Discrete features, we use this model, but in case of continuously varying features, it's not very useful. Yes, the answer is vector. Okay, this you have to keep in mind that it's not a continuous space that we are discussing, rather it's the continuously varying features that we are talking about. Okay, that confusion can be there, that's why I just put it out there. In terms of positional accuracy, dash model is good. For position, understanding the position and everything, this model is good. Which one? Vector, raster, 10 or 3D? Okay, the answer is 3D. Oh, okay, I'm sorry. The answer is vector. Okay, my mistake. The answer is vector. Vector model gives you good positional accuracy. Okay, so this brings us to the end of today's session. I'm really sorry for the inconvenience that happened in between. I'll try to uh, make sure that in the upcoming sessions that doesn't happen. Okay, so are there any further queries? You can ask from this week or the previous week, it doesn't matter. But if you have any questions, you can feel free to ask, or if not, like in the upcoming sessions, also you can ask me. Okay. Hmm. Okay, so if there are no further questions, then we can conclude today's session. I'll make sure that the next session is a little more smooth compared to today's without any interruptions. Okay. Okay. So, yeah, we'll conclude today's session. Thank you so much for listening patiently, and I'll be sharing these slides and video in the link that is available on the portal, so you can easily access it for those who have missed it, and for those who have attended, it will be a recap. Okay. Thank you so much.